Welcome. This video I'll introduce cylindrical equilibria, in particular the theta pinch, which is an early form of fusion research device, not actually used now for reasons that I'll go into, but it allows us to look at slightly more complicated examples of ideal MHD equilibria, which will be useful later. It also introduces some concepts of plasma beta, which is the ratio of fluid pressure to magnetic pressure, and introduce some ideas of diamagnetic current. So what we're looking for is solutions to ideal MHD force balance, which gives us that J cross B is equal to grad P. So we have a fluid pressure gradient and it's balanced by a Lorentz force. And so this time we're going to look at a cylinder like this. So we have a cylindrical geometry. This is usually called Z, down the axis of the machine. And so we have the idea is we have a high pressure in the middle and a low pressure on the outside. And so the radial coordinate here is going to be called R, and the angle coordinate, which I'll draw around here, so this angle coordinate is theta. And what we have in this geometry is you have a magnetic field which is just down the axis, so we have a B which is going this way. So we have B is equal to some function of radius times in the Z unit direction. So B is down the axis of the machine, so we have some external coils which produce a magnetic field in this direction. We have a plasma column in the middle, and then there is actually, as it turns out, a current running in the theta direction. So the plasma generates a current in theta, and together the current in theta and crossed with the magnetic field in Z produces a force in the radial direction. And so that can balance a pressure gradient. And so we have a high pressure in the middle and a low pressure on the outside. So see how this works here. So if we assume we have a magnetic field of this form, we can write down the current. So we have J is 1 over mu naught curl of B from Ampere's law. So we can write this down in cylindrical geometry. And so we have, this is 1 over mu naught. So the radial component is just 1 over R dBz by d theta minus dB theta by dz, and that's in the R direction. Now expect that because J dot grad P must be equal to 0, this should be 0, and if we see here that everything is basically constant in theta, so d by d theta. So d by d theta goes to 0. So everything is symmetric in theta. So that goes to 0. There's no magnetic field in theta, so this also goes to 0. And then we have 1 over mu naught. So now we have the theta component of the current, which is what we should. So we should have a current going around in theta. So a dBr by dz minus dBz by dr. That's in the theta direction. So now assuming everything is constant in z, so we also have d by dz also goes to 0, so that bit is 0, and so we just have this term here. So bz is a function of r. So then we have the z component, so we have a 1 over mu naught, we then have 1 over r d by dr of r b theta, and then minus 1 over r dB r by d theta. And that's in the z direction. So in the d by d theta goes to 0, and there's no b theta, so this term goes to 0. And so the only thing that's left is actually this term here. So we have this bit. This bit here is the only term left. And so we have that J is just 1 over mu naught minus dBz by dr. It's in the theta direction. So a current running around in theta, we have a magnetic field down the axis of the machine, and this is going to provide a radial force which will balance the pressure gradient. And so we can write down that J cross B equals, now we have this first term, so minus 1 over mu naught dBz by dr, times theta, and then this is crossed with BZ in the Z direction. So theta cross Z is R, so we have theta cross Z is R. These are all unit vectors. And so this is just minus 1 over mu naught. And then we can do the same thing of bringing this, as we did in the last video, of putting this b in here to become b squared. And so this becomes a d by dr of b squared, bz squared over 2. And this is in the radial direction. And see, this is a magnetic pressure. Same as in the slab geometry, you have a magnetic pressure which will balance a fluid pressure. And so this is equal to grad P. So this is equal to grad P. And if pressure is only in the radial direction, see this is providing force in R. So we must have that this is dP by dr in the R direction. And so we have, for equilibrium, we can join this term here for the magnetic pressure to this term here for the fluid pressure, and we have that d by dr of the fluid pressure plus the magnetic pressure was bz squared over 2 mu naught, and that's equal to 0. So pressure, fluid pressure plus magnetic pressure are constant. And so we have an equilibrium, we'll draw this again, where we have a cylinder with a current running down in, let's see, the current is in the minus theta direction, so the current is running down this way, so it's g theta. We have B in the z direction, grad P, which is pointing inwards, so grad P like this. We can draw some profiles of this. So as a function of R, R is this radial coordinate out here, so R is this. So I can plot R on this axis, and here I put the pressures. So you want a high pressure in the middle, so a high fluid pressure in the middle. So say P is going down like this. So here we have, this is fluid pressure P. What we have is, on the outside you have a magnetic pressure. So you have away from the plasma, say you have a high magnetic field pressure. So this is B squared over 2 mu naught. And then inside the plasma, so inside the plasma edge here, the sum of these two must be equal. And so as the plasma as the fluid pressure increases, the magnetic pressure decreases. So you end up with a drop. And so the total remains the same. And so you have a high magnetic pressure outside which falls inside. And so the total is conserved, and so the maximum pressure you can get, so the maximum P you could ever possibly get is the pressure outside. So if you have a high magnetic field on the outside, you can get a high pressure in the middle, and the maximum is when you reduce this total field to 0. So you could get a case where you have, for example, this is an R, this is again the pressure. If you have a high fluid pressure, you have a high magnetic pressure on the outside, and then you reduce magnetic pressure here to 0 on the axis. And so in this case, the fluid pressure would be equal to the magnetic pressure. So this is P, and this is B squared. So maximum pressure is the B external. So this is the external field squared over 2 mu naught. And so there's an important quantity which is the ratio of these two, and this is the plasma beta, and it's essentially the ratio of the fluid pressure to the magnetic pressure. And it's essentially a measure of how efficient a scheme is for confining plasma, because what you want for fusion is a high fluid pressure, but what you need to pay for, essentially what you need to build the equipment for, is to make a high magnetic pressure. And so ideally you want this beta as high as possible, so that you get the maximum fluid pressure for the smallest magnetic pressure. And in this case, the maximum beta is this P divided by B squared over 2 mu naught must be less than 1, because you can't reduce the magnetic pressure to less than 0. Okay, so in a theta pinch, what happens is you have a cylinder of plasma, you have an external field, so you have a field running down here, so this is B. What you do in the experiment is you'd start the plasma and then you'd increase the magnetic field over time. And as you increase the magnetic field, the external pressure would push on the plasma and it would compress the plasma. So you start with a large cylinder of plasma, you increase the magnetic field and compress the plasma. And so this compression would heat the plasma. And the hope was to be able to reach fusion conditions. Unfortunately, plasma moves extremely quickly along magnetic fields, and so this is like compressing. This is compression of the plasma by increasing magnetic field. But because the plasma flows along magnetic fields really easily, what would happen is that the plasma would essentially leak out the ends. So you get these cool things called end losses. So as plasma is squashed and compressed in the middle, it squirts out the ends, and so it turned out to be essentially impossible to reach fusion conditions in this kind of geometry. Okay, now in this geometry we have the magnetic field imposed from the outside, and it's being combined with a current running in the theta direction. And so what we have here is the magnetic field on the outside, and then it's reducing inside. And so this is called a diamagnetic situation, where we have the currents in the plasma are reducing the external field. And so the current running on the outside, so we have this cylinder here, we have field running down this axis, and we have this current J theta running around here. So this is called the diamagnetic current, because it reduces the external field. And so I'll do a talk very shortly on how to drive this and where it comes from.